Today we are here with the third episode of Infinite Layers, and we're here with the Lagrange team. And Lagrange, I'm not going to try to explain it, but I've been listening to a lot of the talks from Ismail and his team. One of the more interesting ones, if you're like wanting to learn more, the Roll Up podcast had a nice interview, and I think we're going to touch on a lot of that stuff here and dive into some other things maybe that will be based on some of the questions that we ask. And we're going to be giving a nice presentation into what Lagrange is. So welcome to the show, Ismail and Babis. Do you mind introducing yourselves?
Yeah, thank you so much for having us, guys. And I appreciate the shout out of some of our prior podcasts. I feel like there's been very few people on Twitter who's been able to as succinctly explain what we do as you have, Nader. But so my name is Ismail. I'm one of the co-founders of Lagrange. At a very high level, what we focus on is two core products: our state committees, which are light clients for optimistic rollups, and then our ZK coprocessor, which is a tool for being able to compute very large things in zero knowledge over on-chain data, and then to be able to verify that computation back on-chain. And I'm joined here by Babis.
Hello, everybody. Thanks so much for the invitation. My name is Babis Papamanthou. I'm an associate professor of computer science at Yale and co-director of the Yale Applied Cryptography Laboratory. I am also the chief scientist at Lagrange Labs, where I'm spending currently my sabbatical. I'm leading the research efforts in Lagrange. My area of research is cryptography and computer security. In particular, I'm interested in designing protocols for verifying and securing computations that take place in untrusted environments, such as blockchains, cloud servers, and so on.
Very cool. I would love to know how you all met each other.
So I read a few of Babis's papers, specifically his VSQL paper, IntegraDB, hyperproofs, and balance proofs. And then I reached out to Babis about a year and a half ago at this point, because I felt that a lot of the research that I had seen him pursuing was very applicable to some problems that I was personally seeing in the blockchain space. And this was before Lagrange was really much more than an idea. And then Babis was nice enough to respond and then to meet with me. And I think over that part, we developed a relationship, and Babis joined Lagrange very early in Lagrange's life to lead the research at Lagrange, and has been a transformational figure in shaping the company's research direction.
Amazing. Yeah, I have questions about working with and being part of Yale and the Ivy League schools and all that, because that's kind of fascinating to me, but we'll get to that later. For now, though, I think it would be really cool for us to do like a deep dive or at least an introduction to what Lagrange is. And then when we're done, we're going to ask a bunch of questions. And then if we have time after that, get to more things that are maybe not 100% Lagrange related, like some of my questions about Yale.
I love that. And so I can give a description of Lagrange in my own words, and then I'd love Babis to give a more accurate and technical description as well. But in my own words, the way I see Lagrange is as a series of protocols that make it efficient and low cost for developers to verify types of expensive computation, both on historical single chain state and in complex multi-chain states in their smart contracts in a way they otherwise would have not been able to.
Babis, do you want to add anything to that before I ask a couple of quick questions?
Yeah, absolutely. I mean, one of the main bottlenecks in computing this compact proofs for computation has been the prover time. And at Lagrange, we took a different approach of, focusing on parallelizing the prover and building a distributed system for provers. And this seems to be something that, kind of helps us enable a myriad of new applications on the blockchain that we believe previously were not possible to do, right? And I can get more about the technical stuff and how all of this works, but I would say this has been our main focus, right?
Yeah, I think some of the interesting things that would be hopefully relating to a lot of the people watching this, which are going to be probably a lot of developers, are kind of like the use cases that are enabled by this. And I think there are like some analogies or even some examples of things that you could have done in the past that you can also do either with Lagrange are faster or better or cheaper maybe with Lagrange, and then there might be additional use cases that are kind of opened up.
Yeah. So I love that framing because I think everything you build is defined by what it can do. And with what you can do with Lagrange is to take heavy computation that you would otherwise use in blockchains and you would do maybe a centralized fashion, and now be able to verify that in a decentralized fashion. So, to make it concrete, what types of heavy computation do we do on chain, or do we rely on chain today? And so, simple one would be points programs. I think that almost every application in crypto today, in some form or another, whether that be through explicit points or through implicit airdrop kind of hinting, is trying to drive some form of adoption to their protocol through kind of using their token as a mechanism to incentivize. And that means that a lot of these incentive structures are computed right now off-chain. And they're heavy computation over on-chain activity, but that can't be done in your contract. You can't issue a contract that says, if you transact on my protocol 10 times over the next 90 days and supply X liquidity, you get some relevant reward. It just isn't currently feasible. So that's an example of where you can take a coprocessor, a ZK coprocessor, like what we do, that is instantiated on top of EigenLayer, benefiting from basically all of the trust assumptions you can derive and liveness of this prover from EigenLayer. And then you can render that type of computation and that type of verifiable computation directly to a contract. So points programs, pricing, volatility, all these dynamic DeFi primitives, Sybil resistance for contracts. All of this stuff exists today in one form or another on chain, and it almost all relies on untrusted off-chain compute.
Right. And I can, if I may, can I jump in and say something about the technological challenges of this application we're trying to enable? So we need to expose some computation in a smart contract that refers to some historical state of the blockchain, right? So, state of blockchain nowadays is represented by this headers, like Ethereum header of a block, right? But what's going on is that this uses these hash functions that make it very, very hard and very, very costly to compute any zero knowledge proofs on top of these hash functions. So one of the key technologies in Lagrange is how do we map the state of, say, like an Ethereum block to a data structure that uses a different hash functions that we can use to compute fast these proofs, right? So computing fast these proofs is one thing, but also we have to maintain this mapping from Ethereum state to our state, right? So Lagrange technology, in particular this record trees, allows you to maintain very fast this proof of consistency between the Ethereum state and our data structure, which later will enable us to do very, very fast proof computation, right? So this is basically some of the key technological challenges that we're dealing with to support the application that Ismail was referring to.
And what networks support Lagrange? Like if I wanted to start using it in a smart contract, what networks would I be able to use it on today? And
we are announcing more every week. It's one of our favorite expansion areas. So currently Ethereum mainnet, originally Ethereum mainnet, as of last week Base, as of end of day today Frax, and as of next week a series of other ones. We should be at about 4 or 5 L2s supported by the end of next week. And at the pace that we're going, we expect hopefully to be able to integrate the majority of this in execution space as soon as possible. We've actually already done announcements with AltLayer that we'll be integrating with them. With Omni on their new EVM, we'll be integrating with them. Mantle will be integrating with them that we've announced. We have some other ones kind of in the pipeline that we're cooking up that should be pretty big.
Well, before we get into more questions, do you all want to touch on your presentation?
Yeah. Let me share my screen and we can start walking through that.
Okay, perfect.
Okay. Perfect. Can you guys see it?
Yes, looks great.
Awesome. So, awesome. Okay, so Lagrange focuses on 2 core products. two core protocols. Early on, when you asked what Lagrange builds, the answer that we gave was not proving systems, proof constructions. It was protocols. Because at Lagrange, something that we think very confidently is that in order for the zero-knowledge systems that we build to be relevant and be viable for users, they have to be instantiated as a protocol in a way that other applications or existing protocols can consume. And this is why we build an eigenlayer. The marketplace for trust that eigenlayer provides gives us the ability to instantiate the things that we build in a stateful manner that benefits from the decentralized set of capital stakers, node operators, and the overall ecosystem that will be running and will be participating in our network. And so across what we build, there are the two core products, our state committees and our ZK coprocessor. The state committees are in production today on eigenlayer, supporting two chains, Base and Optimism, and they are a light client for those chains that is able to generate proofs of the states of those chains that can be consumed efficiently by cross-chain protocols who want to originate messages from those chains. And the second product that we build is the ZK coprocessor, which we've been talking a little bit about for the last few minutes, which is the hyperparallel proving system that will very soon be deployed in production on top of eigenlayer. I would assume one of the first proving networks that will be sitting on top of eigenlayer that is able to construct very, very large proofs efficiently through distributing computation and proof creation across series of restaked nodes. And so to touch on the state committees briefly, we pushed the state committees into production day one on eigenlayer, which I think is about 4 weeks ago at this point, or day one for eigenlayer AVSs. Currently, we have about 5 to 6 billion restaked into them to secure the state of the relevant rollups. We have finalized over 2 million blocks for those rollups with proofs generated for them, about 22,000 state proofs, actually 27,000 as of this morning. And we have 40 plus, so currently I think in the most recent committee, 44, 45 operators who are running the infrastructure in order to be able to secure the state from these chains. And so the process of what these operators do is actually very simple. So whenever a new block comes in for a chain, we attest the state, or these nodes attest the state of that block by re-executing the transactions contained in whatever the bash that settles in the DA layer is. And then across those, we're able to generate these proofs of what the state is, or what the attestations were made for those chains. And then we're able to verify those attestations within existing cross-chain protocols. And so this is a very simple diagram of what this looks like. So in essence, a transaction batch comes in to a DA layer, let's say EigenDA. And what Lagrange does is it takes Lagrange nodes, it looks at those transactions, and it executes those as watchers or as rollup nodes. And it then is able to attest to what the state is using their private key and network those attestations across other operators. And across this very large set of restaked operators, we generate a proof of basically that the current committee who's been designated to attest to this state has correctly signed with the correct quorum some relevant block header. And then that committee at that block has been correctly signed off on by the previous block. And so we can basically take this entire relationship of what it means to attest to a given chain, and we can succinctly represent that in a single proof. And we can then take those ZK proofs and state proofs, and we can use those in applications that may, for example, want to predicate some aspect of their security on top of this restake state, this state that was attested to by restake nodes. And so this is an example of what one of these proofs would look like from a pseudocode standpoint. So when we can think of kind of this structure of a block within the Lagrange network as a block header or a group of block headers for a rollup, and the current committee, the next committee, who is designated to sign that block. And then whenever that block comes in, the current committee is expected to sign it with a correct quorum, and the validity of the current committee is defined by having been signed off on at the previous step. So we can look at this kind of inductive proof this creates, and you basically verify the BLS signature of the quorum. You check that every attester key is contained in that quorum and the correct weight within the quorum has signed. And then you're able to check that the current committee for the current block was correctly signed off on by a previous committee. And in essence, the validity of the current committee is only valid insofar as the last committee signed off that was in fact the next committee. And that creates an inductive or a recursive relationship. This is exactly how the Ethereum-like client works on for the Ethereum mainnet, right? You basically have this recursively defined relationship. And so we call this our inductive state proof. And this is kind of a principal component of the state committees. And once we create these proofs, right, like any good proof, it needs to be verified somewhere. And this is where we work with a number of major existing cross-chain protocols to be able to verify our proofs there. And so we currently work with Layer 0 as a DVN. We work with Polymer, and we'll soon to be integrating with Axelar's new amplifier gateway protocol, which we're very excited to do as well. And what we can do is we can take these externally created proofs of what the state of these rollups are, and we're able to then integrate those into existing messaging and bridging pathways to ensure that the state that they're using is backed by a greater degree of economic security than it might otherwise be. And so this is where it's a very synergistic relationship between zero-knowledge proofs and restate security. None or very few existing cross-chain protocols today have 5, 6, or any billion of economic security behind their state. It's very, very difficult to bootstrap without relying on a marketplace for trust like EigenLayer anywhere near that amount of security. And it's also very difficult if we were to just build another Tendermint chain on top of EigenLayer to actually be able to verify what that state is and what these committees are attesting to. So we take this construction of generating a like client and generating succinct proofs, and we combine that with this high degree of restate security, and then we can basically fluidly distribute proofs of that security to cross-chain protocols who want to authenticate their messages based on that. And so that's kind of from end to end how the state committee works. And so this is, in this diagram, one of the things we're talking about here is this kind of idea of you have these fast finality light clients and fast finality state committees, which can be instantiated for any optimistic rollup that builds on the DA layers, from EigenDA, for example, in this diagram, where you basically are able to get your DA security from Ethereum, and then you're very similarly able to get your fast finality or your state security from Ethereum-based collateral. And so Babis can talk a little bit about how we do our updatable BLS application, because one of the things that this kind of construction belies a little bit is the complicated cryptography that underpins it in order to be able to actually have a meaningfully large proof of this validator set. If we have 40,000 nodes eventually in our committee, how do we prove that 40,000 nodes have signed something every rollup block?
Right. So one of the main challenges in this work is to maintain a proof that a certain number of signers that belong to a bigger set of signers have signed, a subset of signers from a bigger set of signers have signed. So typically the way this is represented is the total set of signers is like a digest of a Merkle tree, and then you want to prove that you have an aggregate BLS key that includes a certain number of signers from a specific set, right? So once you compute this proof, now one of the challenges is what happens when some signer leaves that group, right? Typically, in order to recompute this proof, if someone leaves, you're going to have to do it from scratch, right? So one of the things that we're doing at Lagrange is supporting this notion of updatable snarks, where basically, given a snark proof, if part of the witness changes, we can update this proof efficiently. So although we don't solve the problem in its entirety, we solve the problem for specific types of computation, which is MapReduce, and we're able to map this BLS key aggregation to this MapReduce framework, and therefore we're easily update these proofs, which enables this application, because it will be very hard to kind of recompute the proof every time like a signer leaves the group, right? So
does this happen when an operator gets kicked out and a new one comes in? Is that when that happens, or when does that happen?
That's exactly it. An operator gets kicked out, an operator chooses to leave, an operator unsubscribes. The natural entropy happens as part of this set, but it's generally low entropy with respect to the size of the set. Operators don't really want to leave when they're receiving rewards and they're being part of a constructive network, but it does happen. And this is where the updatability means that our computation can be a lot more efficient, a lot cheaper. We can pass those savings down to the cross-chain protocols and the end users doing messaging and bridging actions on these major existing cross-chain protocols.
Right. And again, with every previous approach, in order to keep these proofs updated, you would have to run the snark from scratch, even if only one part of the witness changes, which will not work here, right?
So in terms of this like architecture and this idea, has anyone ever tried to build anything like this, or was it something that wasn't possible in the past?
Yeah, this is a really good question. And I'd say that there's like prior art that gives good basis to the structures that we're doing, but the actual design is very novel because it combines things that are new. So we've modeled the idea of this committee, the current committee, next committee, and then the current block after the Ethereum sync committee, which is a like client for Ethereum. The idea being is that was when we designed this, the current state of the art, and obviously, I think there's going to be some research that's being done into better like client structure, but that was what we wanted to design, to take the current state of the art for Ethereum based like client and instantiate that for other execution spaces. But the question of these proofs, especially generating a proof at the block time of a rollup, let alone the block time of 100 rollups or 1,000 rollups, that's where you start reaching some of these issues in terms of scale. And you'll also reach issues in terms of how you bootstrap the capital behind all of this. If you had to stake Lagrange token and use the prior state of the art of proving, that would just not be possible. It's that intersection of an existing mechanism and innovation in zero knowledge proofs, and then an innovation in being able to have a marketplace for trust that have overlapped to make this product now possible. So
how hard is it to add a new network, to add support for a new network now that the actual system is built?
Yeah, I love this. So a month ago, it would have taken a week. Now it takes 3 days. We expect with the next iteration to take a day or two. And then eventually, I think it'll be permissionless, hopefully towards Q3, Q4.
Amazing. So that would mean in the roll-up as a service world where people are arbitrarily just deploying chains, then they could basically add support for Lagrange.
Exactly. The only tricky part is always the incentives, making sure that they can incentivize enough people to restake into their committee versus another committee. And there's some interesting things we're doing now with, maybe sequencer fee alignment, bridges subsidizing part of the cost of the initial committee and the capital cost, that I think will make it very, very easy to permissionlessly deploy a roll-up alongside a day zero state committee.
Are you done with the presentation part? Can I?
No, we have more.
Okay, cool. Go ahead. Sorry.
One of the things I just really wanted to hop over into before I continue with the presentation was just a demo of our current dashboard. We haven't shown this yet publicly, but so one of the questions that people have asked us recently, they say, okay, you've deployed in production an EigenLayer. What does that mean? What is your infrastructure doing? Who's using this? What is this? Is it attesting to anything? And so the answer to that is yes. This is a fully complete protocol, end to end, deployed on another fully complete protocol, EigenLayer. And so we feel really good about where we are in terms of the instantiation of this, right? These are not just contracts, but they're an actual underlying network reading from the state of the contracts, interacting with the contracts, and feeding proofs downstream from this. And this is something that we're quite excited about. So we developed this Explorer very recently, and we'll be announcing this soon as we kind of polish a little bit the final details to kind of let people really see that, okay, this is up and running. There's AVSs like us, like many of the other AVSs, who are doing real things now on top of this marketplace. And so the top of line numbers, finalized proofs or state proofs generated, batch attestations, total finalized blocks, who our operators are, and who is participating. So we can go to batches, and we can see for every chain, the 2 we support now, but soon to be very many more, And we can see the batches that are being finalized. And we can see, if we want to view details per batch, we can see the chain ID, we can see the L1 block number, we can see which L2 blocks are contained in this batch, right? Because obviously every batch corresponds to a batch of transactions settled in the DA layer, and that's potentially a dynamic number of blocks based on how rollups function. And then we can even see which operators are participating. And this is a very exciting one because we're able to see, who's doing what. And so in the new version of the dashboard that we're coming out with, actually here, the page is already here. We're actually able to see for operators what their uptime is, whether or not they're hitting all their slots, and their current overall performance in the network. And this lets us kind of very easily see who's online, who's not online. And from a user and a delegation standpoint, it lets you assess this. And this is a standard that we're going to be applying across all of the AVSs that we build, including the coprocessor that's coming out very soon, because I think it gives some very interesting transparency, both for operators to see how they're doing, as well as for participants in the network to say, hey, this operator has been doing a phenomenal job. They might not be a brand name, but they're hitting way above their weight in terms of their contribution to this community. And so let's make sure that we're preferentially working with them and supporting them. And the last part I want to show in here is the committees. We can obviously see the epoch numbers since we are this epoch-based designs in which the Ethereum stake sync committee, where we can explore into here and we can see who the operators are. We can see the public keys, we can see the number that there are, and we can see which percentage of them are participating. And my favorite metric here, we can see that we have 44 operators in the current committee. And if we go back and go here, we can see we have 36 operators. So we're trending in the right direction. We're adding new operators every week.
So if an operator opts in, they're essentially now supporting Lagrange across all of the supported networks immediately, like automatically?
That's a really good question. That is part of the design that we've actually decided not to include. So an operator commits to a given network, which makes the load per operator as light or as heavy as they want.
Okay,
an operator can say, I want to run one RPC endpoint to connect to one rollup and one Ethereum thing. I want to dip my toes in being an operator. And they can also say, Lagrange is on 40 chains, and I'm a professional operator who has running tons of nodes. I'm going to connect to every single one. And the rewards scale, obviously, stake requirements scale, but they have agency to decide.
Got it. That makes sense.
And I can switch back over very quickly to finish up some of the slides that we're doing.
There we go.
Perfect. And so in line with obviously the title of this talk and focusing a bit on kind of the coprocessor that we're going to be bringing out and the proving network that underpins that, I wanted to talk a little bit about some of the work that we're doing on the research side, led by Babis, that will let our second AVS, the ZK coprocessor and the underlying proving network, be in production by the end of this month. And so when we say ZK coprocessor, I think this is a somewhat ambiguous term in crypto now. It can mean a lot of things. There's a bunch of different things you can do with them. They're all very different. It's like the word rollup or L1. It can be anything. But what we support is a very specific type of coprocessing. It allows you to basically compute with SQL and verifiable SQL over on-chain data. Think Dune, but you can do verifiable stuff. And then you can verify those results back in your contract. And that's based on some interesting research that Babis is doing on top of our original Reckle-Trees paper. And the current performance benchmarks, I don't really want to get into all the details right now because we can talk about these for hours and hours and hours. We're way faster than the current state of the art for very large computation, right? By orders of magnitude, we're able to excel on that. We can do, in our current performance about a million storage slots computed in a minute 20 seconds if we're talking on-chain verification, maybe a little bit closer to 2 minutes. But like generally when you think of these co-processing proofs, it's usually like 30 seconds per slot, not a million slots.
Wow.
A minute. So that's an order of magnitude faster, thanks to Babis, of course, there. And I think Babis can talk a little bit about some of the work that we're doing with RECL trees and the verifiable database kind of work, and his background in that, of course, too.
Yes, so like I said before, RECL trees is a new cryptographic data structure that has two main properties. First property is that it is naturally parallelizable in the sense that the prover computation can, assuming you have a lot of parallelism, it can be made sublinear. Right, so this is one main thing. And the second thing is that the proofs that RECL trees produce are easily updatable. In other words, if part of the witness changes, you don't have to recompute the proof from scratch. So both these properties are key to Euclid's architecture in the following sense. So whenever you do the transformation from block I, so you get a new block and you want to compute this R data structure, right? So you want to maintain this proof of consistency from R data structure to Ethereum data structure. So this proof of consistency uses the updatability property of RECL trees. So when you go from block I to block I plus 1, the entropy is, if the entropy is small, then you can easily maintain that proof of consistency, right? So once you have this proof of consistency, now you're ready to execute this verifiable SQL on this new tree, on this new Lagrange tree. And there is where the distributed power of RECL trees is relevant, because when, say, you want to do like a join over like big tables maintained in these blocks, then just doing it in an A fashion is going to take forever. RECL trees allows you to distribute this work horizontally and compute these proofs very, very fast. So so these are the main innovations that we're applying in this architecture. And I'm super excited about where this is going to lead us.
Okay, so I'm kind of, this might be a dumb question, but where is the data that's being queried coming from? Like if I have a database that is a SQL database, can I essentially run that query through Lagrange, or is Lagrange actually holding the state and I'm querying from Lagrange?
That's a good question. So what we're doing is compute over on-chain data. So basically, it is the data within your smart contract. Think of the events your contract have emitted, the storage slots of pudgy penguins. A very simple use case is, you're on an L2 and you want to say, show me all users who have a blue penguin. I want them to get a discount in on every time they swap in my exchange. It's Pengoose swap on L2.
But isn't there a way to bring in off-chain data into Lagrange in some way?
There would be, and all of the proving systems that we build would actually be able to compute over off-chain data too. We haven't necessarily focused on that yet, or the first embodiment of what we're doing, just because I think we want to be very laser focused on being able to get the proving systems out and some of the basic constructions on top of EigenLayer and kind of getting operators primed to run their first prover. And that's a very big kind of internal effort that we're putting forward. But there's nothing that precludes us long term from changing, if you see right here, the kind of blockchain input into ZK friendly, or the proof of equivalence from database.
So for example, if you have some off-chain data, you can compute a hash of this off-chain data, include the hash as part of your transaction to the smart contract, and make this off-chain data through the hash part of the blockchain state. So this whole problem boils down to verifying data on chain, right? By representing off-chain data through a single hash.
Got it.
So we will be able to support this operation as well.
How is the indexing done for the data that is queryable then?
Right.
Yeah, that's a really good question. And so what we effectively can do, because we generate proofs of the computation, we don't have to decentralize the indexing. Because in the end, all you get back, every node is like independently indexed, and all you get back is a proof of, hey, this is in fact the correctly extracted data from the chain, and here's a proof that the data was indexed properly, and here's a proof that the data was transformed, and then here's a proof of the query over the transformed data. So you basically end-to-end get back a single proof that asserts the data is correct and the query over that data is correct.
Got it. That makes sense.
It's a very actually exciting design, because you can think of how you can extend this out to a bunch of other applications in crypto. We obviously are very, very focused on the ZK coprocessing right now, but the primitives here, I think, unlock a lot over time, especially as you start kind of thinking of how different AVSs might want to compose on each other. Like, is there an AVS, for example, that might want to consume a proof of what L1 state indexed is?
Yeah, absolutely. And I also feel that, well, I think like essentially, well, the one thing that I'm, I guess, also curious about at this point is,
Mhm.
say, for instance, I'm building out, my next dApp and I'm using
Mhm.
Base and I want to interop with some on-chain forecaster data.
Mhm.
And I want to be able to have a selection set that in the past would not have been easy to aggregate directly on chain because it wasn't a query that was written into that smart contract, but instead it
Mhm.
was a query that was um, retrieved from an indexer that decided to kind of like combine multiple data sources, or I
Mhm.
would say like multiple maybe contract calls to give some, I don't know, combination of smart contract data. Would you be able to kind of compose those sorts of APIs using this?
So what we can compose is anything that's stored on chain. And so if you have, for example, 2 contracts or 3 contracts or a bunch of different contracts with different storage slots or different events or different transactions, you want to create a data structure that composes all of that, we're agnostic to that. Very easy for us. Because as long as it's encoded in the blockchain, we can access it. There's obviously complexities when we're talking about solely off-chain data, because, like, for example, let's say you have an SQL database and you put that SQL database on chain. We can't give any guarantees that you put the correct SQL database on chain. All we can guarantee is that the data in your contracts were correctly extracted and they were correctly computed over with SQL, or actually we can do any MapReduce style computation, and that there's some given result.
And I think we're killing two birds with one stone in the following sense. The transformation that we support not only ensures that we're using a chip has function, but also allows us to reindex and to represent blockchain data in the most convenient way that serves their applications, right? Because remember, we're building and maintaining our own data structure. So we're mapping whatever blockchain data structures there are to our own data structure, and we maintain this proof of consistency that allows us to both be efficient but also to be expressive.
So amazing. Do you want to continue on the presentation, or are you wrapped up there yet?
I will go very fast
No,
because I
no,
know
no
I've been
rush. I
talking
just don't
quite a
want
bit.
to. I don't want to keep the slides up if you're done. Yeah, we have plenty of
Yeah.
time.
One thing I just wanted to touch on was the eigenlayer component, because I see a lot of people talking about the ZK eigenlayer. Is ZK competitive with eigenlayer? Is eigenlayer competitive with ZK? And it's been a statement of Lagrange since day one. It's something that's very important to us, that in fact, these are incredibly complementary technologies once you look at the first principles of them. What you can get with eigenlayer is a retroactive objective flashing condition, which is, in effect, there is an objective set of conditions where if an operator does not perform some task within a specified requirement set, you can assess that they have not performed that task in an objective way. And proving, and liveness of proving, is something that can actually very efficiently be objectively assessed. You can commit to say, I want a proof. I'm going to compute a proof now within time t. And then you can return the proof. And if it's within time t, receive a reward. If it's within time t plus 1, you don't, or you receive some penalty. And so what you're able to do is to build a lot of these conditions into a protocol that takes ZK, which asserts the safety of computation, and it is able to combine that with an economic layer or marketplace for trust like eigenlayer that is able to guarantee the liveness of the proving. And that's something that we get on eigenlayer from how we're deploying our coprocessor and our proving network that's fundamentally unique. And that's something that we're very, very excited about coming to market with very soon. And so this diagram, really quickly, we talk about these provers, and we talk about this hyper-parallel ability to do the proof thanks to record trees and some of the work that Babis is leading on verifiable database design. And we're able to benefit from that scale by having the operators on eigenlayer do that proving to basically source computation way larger than Lagrange could ever access independently. And that's a very big kind of step function. And so the final thing I wanted to cover here is just the developer side of things. And this is an example of what it would look like today and hopefully for the next little bit, for a developer to actually use Lagrange. And so what we see here is contracts that are registered to have their data processed. So you deploy your contract. Let's say it's a popular contract. It's a DEX. It's a lending app. It's a cool NFT collection. It's an ERC20. You basically say, I want this contract. And you start on chain. I want it to be indexed. We're going to pay this much for it to be indexed. And then we're also going to pay for we're going to specify some queries that we support on top of it, right? And these queries are going to be specified as events. So here is the Pudgy Penguins contract. We're going to take all the mapping data and we're going to put that into a relational table, basically. And we're going to prove that the table is correctly formed from the on-chain data. And then we're going to prove a series of select queries, a series of unions, a series of aggregations on top of that. And query 1 is event 1, query 2 is event 2, with some configurable parameters in there. What the developer can then do is say, hey, I want to do something with this state. I want to compose on this state in an interesting way. I want to have Pudgy swap. I want to have, real volatility of a DEX or a series of DEXs. And I want to be able to run the query over this data structure. So I'm going to emit this event. I'm going to configure the parameters that I want. And then I'm going to wait for the coprocessor to return the data. And so here we can see that the user smart contract basically requests that it wants to do a query, registers, takes queries from users. Then you request you want a query. And then what you can do here is you can have the broader proving network that we have deployed in EigenLayer that is able to then compute the data structures, index them, then to prove the indexing is correct, and then to prove a query over the index data, and to combine then the proof of the indexing with the proof of the query to get a final proof that can be verified anywhere you have the block header. And so when it says any other blockchain here, you can think of that honestly as including Ethereum L1. To Gajesh's question, yes. So the coprocessor will be on an AVS within 3 weeks, maybe 3.5 weeks. But that will be very exciting. It's, I think, the first big proven network, hopefully deployed on EigenLayer. Won't be the last for sure. And so we're quite excited about getting the proving network and the coprocessor deployed on Eigen, because effectively we can benefit from a lot of the scale that we can get from the operator sets and the liveness of prover. So user, all they have to do is they call a contract, they emit an event, and they wait for their proof of what the query over that data would be.
And if you want to create the second AVS that you all are deploying, right?
Yes, which will be by end of May.
And that's still going to be under the Lagrange company name, right?
It is.
It's just going to be a different product.
It is. We love AVSs too much. We have to build them.
So when a user submits a query, is that that's a transaction or is that an actual query?
It's a transaction. So the way we've designed it is that a contract can effectively query these. So a contract can basically call a function of another contract and say, I want to do this query. And this contract basically exposes that. What this lets you do is basically circumvent gas limits, right? So if we think of, let's say I want to select all penguins that are blue from the Pudgy Penguins contract. That's pretty intensive. If I had to loop through all 8,000 penguins and check the metadata of every single one, it wouldn't work. You could verify that, and the Frax benchmarks we have, it's 2 cents to get the proof back and verify that.
Nice.
Easy, cheap. Yep. You can compose on state. It can be cross-chain state. It can be single-chain state. But it's just you build a data structure. Yeah.
All the computation can be done offline, and then we just expose online the proof and the result directly that is correct with respect to the blockchain state, right?
Okay, this is a question that I have. Mm-hmm. If the NFT metadata is stored off-chain on IPFS or Arweave, then how do you all actually query that to get that metadata information?
That's an amazing question. And so my metadata example, that was a pretty bad one, because what you would have to also do is you have the commitment to the metadata on-chain, which is a hash of the off-chain IPFS data. So you can prove that you've correctly passed a pre-image of all of those hashes into there and then query on top of that. So it's an additional step that's not represented in this diagram. But a better example would be maybe ERC20 balances, because that flow that we're talking about, we do support.
Yeah, everything is there
very soon. Right. Yeah, but ERC20.
ERC20, yeah.
NFT, we can do that. We just basically, because it's another pointer basically to more data. So it's you have a pointer in memory to basically where the hash of the data is stored. And then you're able to then create a table that proves that, hey, with the next degree of the proof, I've taken that metadata, I've correctly taken that, I've hashed it, and here's the table that includes the off-chain stuff.
Pretty
It's
sweet.
same security guarantees. It's super cool. It's something we're very excited about.
Right.
And Babis can add a little bit of context here because obviously he's way more qualified than me.
Yeah, so as long as there's a commitment of metadata on the blockchain, then part of our proving system can be unrolling this commitment in a highly parallel fashion and computing this proof, and basically using this metadata on chain irrespectively of where they're physically located.
And we're now done with deck.
Okay, cool. That was really good. Yeah, we are kind of we're a little bit over on time actually, so we probably need to wrap it up. But I really appreciate you all coming on and spending the time. I know you're super busy. You all recently raised or announced a fundraise, is that correct?
Yeah.
Can you tell us a little bit more about that?
Yeah. Yesterday, we just announced a fundraise led by Founders Fund. It was a $13.2 million round with participation from Archetype, 1KX, Maven 11, Fenbushi, and Volt, as well as the Mantle Ecosystem Fund, one of our partners, and CMT Digital. And then a number of angels on there, friends, investors, people we've known for a while. And so it's been pretty awesome. Thank you. There's been an outpouring of support that we've been able to receive from the space, and it's been genuinely very appreciated, as all the support we've received from the Eigenlayer team as we've developed both of our AVSs.
Yeah, totally. It's been really cool. I've been with Eigenlayer for only a little over 2 months, but I think you were one of the first people I met building an ecosystem. So it's been kind of cool to see everything you all have done already in such a short amount of time. I know you've been working on this for a long time before that, though. So, Gaj, is there anything that you wanted to add before we start wrapping it up?
Oh, no questions. I think this was really amazing. I think this is something really cool getting built on Eigenlayer, and yeah, let's go.
Thank you so much.
Oh yeah. So if people want to learn more and get started building on Eigenlayer, what would be building on Lagrange, what would be the first steps that you recommend them to do?
Yeah, I think it depends on kind of, if they want to build a cross-chain protocol, ping us and we'll be able to plug our proofs into you right now. If you want to build on our coprocessor, also ping us and we'll be able to plug our proofs into you right now. If you want to be an operator, ping us and we'll help you become an operator. I think from our standpoint, one of the things I feel has been missing in ZK is enough education over running provers. I think that as more people are able to run provers and contribute to the overall computation within a proving network like what we build, the space as a whole is going to become a lot more ossified as something at the core of crypto. And I think with Eigenlayer, you have a perfect place for people who want to run infrastructure to come in and participate in the marketplace and to be contributors to Lagrange's proving architecture. And so we'd love to help anybody who's never run a prover before run their first prover with us.
That's amazing. Okay, so just one last thing. If someone's running an operator that is supporting Lagrange, are they essentially running a prover?
For the state committees, they're not yet. They're just running an attestation node. But for the coprocessor, which will be up by the end of the month, they will be running a prover. And so we're taking people there to try to help them be some of the day one folks who will be running us.
Awesome. Well, thanks everyone for showing up and being a part of this, and everyone that watched this. Thank you. We're going to be doing more of these at least once per week, maybe twice per week like this week. So keep an eye out for those and definitely go check out Lagrange. So thanks for watching. We're going to close it out now.
Thank you guys so much.
Thank you very much. Thank you.